Hi there. During this session I'm going to be talking about nuclear power and its role as a non-fossil fuel option in today's world. So straight away let's think about what you already know about nuclear power. So we're imagining the Simpsons nuclear power plant here. A few things that we get off from the start. So some questions. What fuels do nuclear power stations? Well, the fuels we use are uranium and plutonium. So these are the two options. The process which releases nuclear energy, which we're using in nuclear power stations today, is nuclear fission. And the main advantages of nuclear power are, in some ways, the reasons as identifying the things which fossil fuels do badly. It's the fact that you get a large amount of energy for a small amount of fuel, but crucially there's no acid rain, no greenhouse effect, and once they're up and running, so the cost of building a nuclear power station is quite a lot, but once up and running they're quite cheap to run. So first of all I'm going to think about the process, nuclear fission. Now what happens with nuclear fission is, and we used the example of uranium here, is a slow moving neutron strikes uranium. The uranium goes through a process of fission, which is breaking up into smaller parts. So we've got small daughter atoms produced, and furthermore there's further neutrons released. Now the further neutrons being released is really important, because these neutrons can then go on to start further reactions, causing a chain reaction, so this process carries on indefinitely until it runs out of fuel. Now let's look at a nuclear power station. Nuclear power stations in many ways works very similar to normal power stations. So there's lots of features that you'll recognize. We've got a turbine and a generator and a condenser, and we have a steam generator. Okay. The more kind of, I guess, specific to nuclear power stations is what we have here is the reactor vessel, the control rods, and the heat exchange system. So we'll talk about those in a little bit more detail. Everything else is pretty much as we'd see in a normal power station, but the finer details are. First of all, in the reactor. The reactor contains some crucial parts. It has control rods, which I'll talk about in a minute, moderator, I'll mention in a minute, the fuel, which is going to be plutonium or uranium, and a coolant of some sort, which gets rotated around into a heat exchanger. So let me talk about each of these parts in detail. First of all, the fuel rods. The most common is enriched uranium, and enriched uranium means that it has an increased amount of uranium-235 in the rod itself. Okay, so it's normally uranium, but the amount of uranium-235, that isotope, has been increased by a certain amount. And we'll talk about more when we talk about enrichment in the future. And they tend to be long, thin rods, and they're trying to maximize the area there, so the escape of neutrons is maximized as much as possible. The moderator. Now, as I said earlier, uranium really needs actually slow-moving neutrons to cause fission. Okay. So what happens is that if the neutrons are traveling too fast, then there's not normally an interaction. So therefore we have a moderator. Now a moderator is some chemical, often graphite, sometimes we use as water, but what it does is that this causes lots of interactions with the fast moving neutrons and causes them to slow down. And as they slow down, it increases the likelihood of further reactions. The control rods. Now the control rods are really important because they're used to stop a nuclear fission getting out of control. What they can be done is that they can be lowered into the reactor, and when they're lowered into the reactor, it means that the neutrons are absorbed. They're taken out of the equation. So that means the chain reaction, or the amount of fission taking place, is reduced, and it gives you an opportunity to control the overall temperature of the reactor. These are normally candium and boron rods because they effectively absorb lots of neutrons. The coolant. So the coolant is usually carbon dioxide, but water is used as well. And what it's done is it's passed through the reactor and I guess coolant is a cryptic name in some ways. So what the coolant does is it's used to keep the reactor cool by the heat being transferred into it. So then the hot coolant comes out and that goes into the heat exchanger. And so what happens in the heat exchanger, the energy from the coolant is transferred to heat up steam, and then that steam goes into the turbine and drives the generator, much like any power station we've spoken about before. This coolant then circulates back into the reactor once it's cooled back down again and rotates around. Because it's in such close proximity with the reactor core, it often becomes radioactive. So that's why it's kept as a separate system. The heat exchanger, there's a heating side where a pipe is providing thermal energy to be transferred from the coolant to the water. And so the water expands, causing the turning of the turbines. And there's also a cooling side where the steam from the turbine is cooled down, like in a typical power station. And therefore, this cooling process means that there's some wasted heat there. So hot water is a byproduct of this. And it causes a thermal pollution of sorts. Efficiency. So if we think about the efficiency of lots of power stations, we can sometimes useful to think about it just by looking at the amount of energy which is usefully converted. And because we're talking about a hot situation and then it cools down again, what we can do is if we have a hot reservoir and it's cooling down to a cold reservoir, that means all that energy is being dispersed in some way, and you want some of that energy being dispersed to be converted into work. Now, so if you understand the temperature difference, it means you can work out how efficiently your engine is working, or your generator is working. You want it to have as much work being done as possible. Thinking about thermal efficiency, we can think about the useful work obtained divided by the heat input from the hot reservoir in the first place. So QH is the heat energy. This could also be worked out as QH, which is the heat energy going in, minus the heat energy which is coming out in the coolant, divided by the heat energy. So my example is a reactor is kept at 570 K, and the water in the secondary loop is returned to the boiler at 310 K. So I can subtract and find out the temperature difference, and divide that by the value for the hot reservoir, and I can work out the efficiency. In this case, it's 46%. So, nuclear power, is this the solution for everything? Well, there's some disadvantages. Here's a picture of the Chernobyl nuclear power station after it exploded, and there's obviously some quite serious considerations that have to be taken for safety. Other things to think about. It is expensive to build in the first place. It's very expensive to decommission. Once you come to the end of the lifetime of a nuclear power station, you have a lot of radioactive stuff which needs to be disposed of in a sensible way. Radioactive waste itself. Once the fuel has been used, we have still a whole pile of quite radioactive substance which needs to be disposed of in some way. Quite often this involves sealing in containers, then burying very, very deep underground. There's an association with the increased radioactivity associated with nuclear power stations and cancer. And the other thing is there's a huge amount of water required for the cooling purpose. And that means there's a lot of hot water, which in some cases released into the environment has a very negative effect. It's in some ways non-renewable. It's a non-fossil fuel, but once it's used up, it's gone. And there's also some issues with mining. Some of the places where you can get this, unfortunately, don't have the most stable governments in the world. And there's always a risk of a disaster. That's something we should never forget. On top of that, we have a situation or have a resource here which could be misused. So risk of military and terrorist attacks.